Hi everyone, welcome to CS 188 Section 9, and today we'll be talking about HMMs and particle filtering. So first, we're going to go over HMMs, which stand for Hidden Markov Models. So first, let's just start off with what's a Markov model. So in a Markov model, it's a specific form of Bayes net in which we have variables that are indexed by time. So we'll have x1, which is our variable at time 1, and variable x2 at time 2, x3 at time t, and so on and so forth. And the way that this Bayes net is drawn is under the Markov assumption, so that the current state only depends on the previous. So what does that mean? That means we just draw horizontal arrows like this. So x2 only depends on x1, the time before, and x3 only depends on x2, the time before. And this goes on and on. So now we talk about hidden Markov models. So in hidden Markov models, we don't actually get to observe these x's. What we do observe are these hidden variables, or these evidence variables. So at time step 1, we observe E1. At time step 2, we would observe E2. At time step 3, we would observe E3, and so on. And the assumption we make in HMMs is that the evidence only depends on the state at that time step. So E1 only depends on x1, E2 depends on x2, and E3 depends on x3. So what I mean by depends is that E2 is independent of all previous states given x2. Okay, so now, and also let me shade these in to show that we observe these evidence variables. So one example might be xt could represent, let's say, rain, but maybe all you get to see are people bringing umbrellas. So based on seeing umbrellas, you need to infer whether it's raining or not. So now that we have this model, what do we actually want to compute about it? Well, what we want to compute is the belief for a given hidden state xt. And what is this? This is going to be the probability that we're at that state given we've seen all the previous variables. So you can think of this like weather. So let's say I've seen E is my weather and I've seen it for the past 100 days. Now xt, you're trying to say, oh, what's my belief over the weather today? So now, because what we're going to do is we're going to calculate these beliefs, and we're going to take advantage of the structure of the Bayes net, of the HMM. So we break it up into two steps. So first, we have we call it the passage of time. So we're going to start off with, we assume we're at some xt. So we have both the belief of xt. And now we want to go one step further. So the probability of the next state, xt plus 1, given still just my evidence, I've got no new evidence. So this equals the sum over xt of, we assume we know, I should say first is we assume we know the transition probability. So we know the probability of xt plus 1 given xt. And we also assume we know the evidence probability, which is the probability of evidence et given the current state xt. So now let's go back to the passage of time. So the probability of xt plus 1 given all of my previous evidence is starting from our current belief, probability xt given 1 to t, and we push it through the transition probability. So the probability of xt plus 1 given xt. So as you can see, this is just marginalizing. So this is the same BaseNet operations we've always been doing. So I can also rewrite this just using a notation change as this is actually the belief of xt, which we already calculated. We assume we know that since we're doing recursion. And then the probability of xt plus 1 given xt, which we know because it's the transition probability. And to make this simpler, we actually define this as b prime of xt plus 1. So that's just notation. So now that we've done the passage of time, which is basically if we, let's say we started at x2, then what we just did is now we moved forward to x3. Now what do we need to do next? We need to incorporate this evidence. So I can color code this passage of time. And now we're going to do the observation update. And this is what's in red. So now we want to compute is the probability of xt plus 1 given e1 to t plus 1. So we've got another piece of evidence. And this is going to be proportional to the probability of xt plus 1 given e1 to t times the probability of the new evidence t plus 1 given xt plus 1. And this is using conditional independence assumptions of the HMM. And we can also rewrite this as belief prime of xt plus 1 times probability of et plus 1 given xt plus 1. Okay, so this is how you do the how you calculate the beliefs for hidden Markov models. You do passage of time, you do the observation update, and you just repeat this starting from x1, and then you go to x2, x3, and so on and so forth. Okay, so now we're going to look at a sampled version of HMMs, which is called particle filtering. So in particle filtering, we assume we also have a transition probability. And we also have an observation probability. But we track our distribution through samples. So for example, let's say you have a grid and we want to determine, we want to have a sampled belief over where, let's say, where Pac-Man is. So we're going to have multiple hypotheses. So for every single blue dot, that's samples of where I think Pac-Man could be. So in this, I'll make this a little nicer. So in this example, our distribution would tell us there's a 1/2 probability Pac-Man's in the top right corner. So now what we want to do is we're going to use the same exact BaseNet, the same exact HMM structure in which there's a passage of time. And then there's also an observation update. Now these will be slightly different than from before. So the passage of time, instead of computing a belief, we operate on the individual samples. So since we're going to be using the transition probability, that's what passage of time is, moving one step forward, we just, for each particle, we sample a new particle x prime, and that's sampled from the transition probability of x prime given x. So once you do passage of time, you'll get a new board, a board with the particles moved. So for example, let's say I'm doing passage of time on this particle, and I sample it, and maybe it might move to this square when I sample it. So you do that for all the particles. Now for the observation update, you assign a weight to each particle. So we're in this new grid over here, in which we've done the passage of time, and we say the weight of the new particle x prime is the probability of the evidence, because we received an evidence. We received an evidence measurement given the new particle. Okay, so now we have a distribution of samples, and each one has a weight. But now we do one last step. So what we actually do is now we resample the particles according to their weight. And this is going to be exactly or very similar to likelihood weighting, which we did before. So for example, let's say I have, weight equals 0.1, and weight equals 0.9, weight equals 0.9, and maybe the sample is at coordinate 3, 2, maybe there's one at 3, 3, maybe there's also one at 3, 3. So I would sample the first particle with probability 0.1, or 0.1 plus 0.9 plus 0.9, and I'd sample the second one with probability 0.9 over 0.1 plus 0.9 plus 0.9, and on and on. So these are the three steps that you do, and after you resample, you'll be back to a grid with a bunch of particles all having weight 1. And in the worksheet, we'll go over how to actually do these